Okay, modern. Modern physics. This one's kind of heavy on the conceptual and a bit of some of our equations too. So absolutely important equations for this section are going to be the energy of a photon. Energy of a photon equals Planck's constant times the frequency of the light. A photon is a particle of light. We found out from photoelectric effect and Einstein coming up with an explanation of it that we kind of had to see light not simply as a drawn out wave but as a single particle coming in. So that was one of the big conclusions we got from that. A lot of modern is built around the idea of wave-particle duality. It turns out that light, which we expected to be a wave, sometimes acts like particles, and it turns out that things like electrons, which we know are particles, also sometimes work like waves in very strange ways. All right, so next important one, this is actually one that we borrowed from wave mechanics so that we could use it. Our velocity of our wave equals our frequency times our wavelength. Okay? And so whenever you're dealing, usually in modern, the wave you're dealing with is usually light. So this is often equal to c, where c is the speed of light, 3.0 times 10 to the 8th meters per second. Next one. This one deals specifically with the photoelectric effect. Our maximum kinetic energy for an electron being ejected off of a metal. Basically, we have a photon come in, a bit of light that has some energy. The electron absorbs that energy, and it's plenty enough to send it flying off into space. So, the kinetic energy that it ends up with, the maximum that it has, is equal to the energy of that light, hf, see, that's coming back up, minus what we call phi, the work function. And the work function, for all intents and purposes, is effectively your ionization energy. Now, don't rely simply on being able to identify it as ionization energy, because in physics, for this specific setup, we always call it, well, usually call it the work function. So you want to make certain that you're able to pick up on that phrase and know how to use it. You can either find the work function, which is the amount of energy you need to rip that electron off the atom, or they may give it to you. And when they do that, they'll say the work function is this in probably electron volts. You need to know what to do with it. And if all you're thinking is that this is the ionization energy, that may not help you. Work function. But for the most part, they're effectively the same thing. Finally, we have something called the Broglie Wavelength. This deals with both our finding a way to find the momentum that light has, because strangely enough, light does have momentum. We got that from Compton scattering, where we put light through a cloud, and then we noticed that at little diffraction angles, it would ever so slightly change its wavelength. We were able to piece together this equation, where our momentum, P, equals Planck's constant divided by our wavelength. Another way of writing this is our wavelength equals h divided by our momentum. What we later went on to discover was this also holds with particles to find their equivalent wavelength size. I said that our electrons have a tendency of acting like waves on a regular basis. If we know what their momentum is, we can actually find what their wavelength is. We can know something about how they're going to act like a wave. Finally, the last equation, and this one should probably be something that I expect you probably already know. It's mass energy equivalence. E equals mc squared. Now, we talked about this a bit in class. It is easy to sidestep the actual power of this equation, that there's such a ridiculous amount of energy stored up in the smallest amounts of mass. Now, some of the ways that you may see this is delta E equals delta m times c squared, where it's change in mass. Basically, you're looking at an object, then you check back after it undergoes, say, a nuclear reaction, and it's lost some of its mass, and that has gone into the energy that it has released. But for the most part, it's just E equals mc squared. You find out the mass that you're losing, maybe a kilogram, which is way huge, but you plug it in there, multiply it by the speed of light squared, and that's how much energy you get out. Or, if you want to find out how much mass you could get, if you could condense the energy down, you plug in the energy here and solve for mass. All right. Pardon me. Big ideas. Wave-particle duality. Started off with light. We knew light was a wave, and then Einstein came in and basically told us, hey, for this photoelectric thing to work out, let's change the paradigm. Sometimes this wave acts like a particle. That way we could explain why it didn't matter how much light we put onto a metal, all that mattered was really the color involved. Remember, that red laser, no matter how bright it was not lighting up that glow-in-the-dark material. Neither was the green laser. Only the violet did. We got that material to light up really bright when I got out that small lamp, that really dim lamp, because it had enough energy. It doesn't matter the intensity, only matters the energy of that light. Because of that, we came up with wave-particle duality for photons. Later on, because of some other experiments, we actually found that electrons do the same thing. We thought they were particles, and it turns out that those sneaky little devils actually act like waves on a regular basis. Now, some of the equations that I had you solve with the Broglie wavelength, I had you find the wavelength of a person jogging. I had you find the wavelength of a car going down the highway. Most likely, you got a number so fantastically small that it's arguable if it even means anything. Anything on the large scale, like you or me or this notebook, it's not going to have a wavelength on the appropriate sizes where it can actually really act like a wave in any way that we can actually identify it. Okay, so wave-particle duality. That's a big one, although, like most things in modern, it's kind of difficult to wrap your head around. Photoelectric effect, which we talked about. Be kind of familiar with it. It goes along really well with our energy diagrams. So we took a look at a lot of those. We had something where down here, 0 electron volts is our ground state. Maybe up here at 1.9 electron volts, we have an allowed orbit. Maybe up here, 3.4 eV. And we have an electron that can hang out in any one of these. But, nowhere in between. It cannot be in any of the spaces other than on these lines. With the exception of, if this is the highest level, it can go flying off into space and become a free particle. You're free, boy. Free. But when it is bound on these, it can only be on one of these shelves or the other. We can't have it suspended magically in between. Again, this is one of those weird wave properties of that electron. It only has discrete things that it allows to happen. Photoelectric effect basically says you've got to have enough energy in your light coming in to eject this guy off. You could have all the light in the world, but if it's not a high enough energy to get this guy to jump off, then the electron's not going anywhere. Alright, so the next thing which ties directly into this is discrete spectra. We talked a lot about this. This is when you burn an element or you look at an element being energized. Each of them have their own very specific colors. And all of it is explained by this guy up here, these same energy levels that we were talking about just a moment ago. That's why those are so common. Discrete spectra. Now this is at the heart of quite a few different things. It is one of the ways that we actually can know the composition of stars and other parts of the universe, things like nebulae out there, very distant objects, that sort of thing. It's all of these little fingerprints that relate to the energy levels that change for each element. And if you remember from class, I made the connection that these energy levels, we've got the electron here and then some nucleus down here, some positive charge and negative charge, and these are all point particles, at least how we're imagining them there. So that's where that Coulomb stuff comes back in. All right, discrete spectra, those are important. Finally, we talked about decay, different types of nuclear decay. We had alpha, which is the emission of alpha particles, which are helium nuclei. We had beta, which is the emission of an electron or a positron, which I almost wrote the wrong thing. A positron is usually little e plus. Yay, antimatter. And then finally, a gamma decay, where we release an incredibly high power, high energy, I should say, photon. Usually in the gamma ray end of the spectrum, hence gamma. So be familiar with decay and types of radiation. Remember our notation where we had the atomic mass, we had our element, and we had the atomic number. Where this guy is, so for instance, when we had uranium 92 and 238. 238 is its atomic mass, its elemental symbol is U, and then 92 is its number. That tells us how many protons are in the nucleus, which defines it as uranium. The final thing to keep in mind on that is the rules that govern nuclear reactions. There are two of them that we're dealing with anyway. One is conserve atomic mass, or as I like to call it, conserve nucleons, the number of particles that normally are found in a nucleus. So if you start off with 20 protons and neutrons, you have to end with 20 protons and neutrons, right? We could have a proton become a neutron or a neutron become a proton. They can change, but we still have to have the same total. The other one is conserve charge. So if we have a neutron that manages to morph itself into a proton during a nuclear reaction, which does happen from time to time, then we will actually have, we started off with a neutron which has 0 charge. We ended up with it becoming a proton, which is a positive charge. So to conserve charge, we must also create and kick off an electron in, wait for it, beta radiation. You will also see that's why I have this positron listed here, because when you have a proton become a neutron, you started off with 1 positive, then it goes to 0, we will actually have a different form of beta radiation, the positron, to conserve our charge. Alright? But with all of that, that should be the main stuff that you need for modern.